You think there's no gravity in space. It's the most natural thing in the world to believe. You've seen the footage 1,000 times. Astronauts drifting through the cabin, tumbling in slow motion, chasing floating water blobs with their mouths open. And the explanation seems obvious. Up there, gravity runs out. You get far enough from Earth and it just lets go of you. Here's the strange part. That's not what's happening, not even close. The space station orbits about 250 miles up. And at that height, Earth's gravity is still pulling with about 90% of the strength you feel standing in your kitchen right now. If you weigh 100 pounds down here, you'd weigh about 90 up there. Gravity isn't gone. It's almost all still there. So why do they float? Because they're falling. The whole station is falling toward Earth constantly, and so is everyone inside it. But it's also moving sideways, fast, around 17,500 miles an hour. And here's the beautiful trick. It falls toward the ground at exactly the rate the ground curves away beneath it, so it never gets any closer. It keeps falling and keeps missing. Forever. Everything inside falls together at the same rate. The astronaut, the water blob, the walls, so relative to each other, nothing seems to fall at all. They just hang there. That's the float. It isn't the absence of gravity. It's the purest surrender to it. The moon is doing the same thing right now, falling around us and always missing. So that's number one, and once you see it, a lot of space starts to look different. Let's keep pulling. You've heard space is silent, total nothing, no sound at all, and for your ears, that's basically true. Sound needs stuff to travel through, air, water, something, and space is nearly empty. A supernova could go off and you'd hear nothing. The tagline was right. In space, no one can hear you scream. But space isn't perfectly empty. In the dense gas that fills a giant galaxy cluster, real pressure waves can ripple through. There's a black hole in the Perseus cluster that's been sending out sound waves for ages, a note so low it sits about 57 octaves below the middle of a piano. A real note, a B-flat you could never hear. When NASA lets you listen to it, they've shifted it up billions of times just so it reaches human range. So space is silent, yes, mostly. With one impossibly deep song you were never built to hear. Now cold, everyone knows space is freezing. Step outside the airlock and you flash freeze in an instant, right? Not really. Here's the thing about cold. Temperature is just how fast molecules are jiggling, and to feel cold, something has to pull the heat out of you. On Earth, air and water do that fast, which is why a cold lake steals your warmth in minutes. But space has almost no molecules to touch you. The only way you lose heat is by slowly radiating it away, and that's sluggish. You would not freeze fast. If anything, the opposite. Sit in direct sunlight up there and you overheat. Spacecraft carry radiators to dump excess heat. The sunny side and the shadow side of the same object can differ by hundreds of degrees. Space doesn't really have a temperature the way a cold room does. It just refuses to take your heat quickly. Which brings us to the big one. What actually happens to a human body exposed to raw vacuum? The movies give you two options. You explode or you freeze solid. Both are wrong. Your skin and tissue are strong enough to hold you together against that pressure. You don't burst, and you don't freeze for the reason we just covered. What does happen is stranger. With no pressure outside, the water in your soft tissues and on your tongue starts to turn to vapor. Your body swells, but it holds. The real danger is your blood dumping its oxygen almost instantly. You'd have maybe 10 to 15 seconds of useful consciousness. Then you black out. And if no one repressurizes you within roughly a minute and a half, that's the end. We know this because it nearly happened. In the mid-1960s, during a NASA test, a technician named LeBlanc had his suit lose pressure inside a vacuum chamber. He stayed conscious about 14 seconds. His last memory before passing out was the saliva boiling on his tongue. They repressurized the chamber. He recovered. His only lasting complaint was a sore ear. A man met the vacuum of space and walked away with an earache. Let's do a gentler one, the Great Wall of China, the only human structure you can see from space. You've heard it your whole life. It's one of the hardest things up there to spot. The wall is long, sure, but it's only about 15 to 30 feet wide, built from local stone and earth that blends right into the landscape around it. Long, thin, and the same color as everything beside it. From orbit, nearly impossible to pick out. China's first astronaut looked for it and couldn't see it. Astronauts from other missions said the same. And the myth is older than spaceflight itself. People were claiming you could see the wall from the moon back in 1754, and again in a 1932 cartoon, decades before a single human went up to check. It was fiction from birth. Meanwhile, from low orbit, you actually can see highways, airports, big dams, the wakes of ships, and cities glowing at night. Just not the one thing everyone swears by. Here's when you can check the moment you step outside. What color is the sun? Yellow, obviously. Every drawing you made as a kid had a yellow sun, but the sun is white, actually white. It pours out every color of visible light at once, and mixed together, that's white. Astronauts above the atmosphere confirm it. Up there, the sun is plainly, cleanly white. So why does it look yellow to us? The atmosphere. Air scatters blue light more than the other colors, flinging it out of the sun's direct beam and spreading it across the whole sky. That scattered blue is why the sky is blue, and with the blue pulled out, what's left of the sun's beam looks a little yellow. The yellow sun and the blue sky are the same thing seen two ways. Near sunset, when the light travels through even more air, that effect cranks up and the sun goes orange, then red. Every sunset you've ever loved is just the atmosphere sorting light by color. Now look up at the moon, the dark side of the moon. You've heard that phrase forever. There's no dark side, there's a far side. The moon spins exactly once for every trip it makes around us, so the same face always points our way. The other hemisphere is simply the one we never see from home, but it gets just as much sunlight as the side we know. 2 weeks of day, 2 weeks of night, all over the moon. Dark never meant unlit, it meant unknown. We didn't lay eyes on it until a Soviet probe photographed it in 1959. And here's the twist. That far side looks like a different world. Far fewer of the dark, smooth plains we see on the near side, and far more craters. It's actually brighter than the face we know. And why the two sides came out so different? Scientists still argue about it. That one's genuinely unsolved. 2 more. When a meteor streaks across the sky, blazing white-hot, what's heating it up? Friction with the air, right? Rubbing against the atmosphere. Mostly no. The real culprit is compression. A meteor slams into the air at more than 11 kilometers per second, so fast the air can't get out of the way. It piles up and crushes into a shock wave in front of the rock, and squeezing air like that makes it ferociously hot. That superheated wall of compressed air is what lights the meteor up. Friction is a minor player. And this is the part that stops people. The meteor itself is cold. It came from the deep freeze of space, and only its thin outer skin ever heats up in those few seconds of entry. Which is why meteorites, freshly landed, aren't glowing lava. Some hit the ground cold, even frosty. A rock that just tore through the sky as a fireball, cool enough to pick up. Now where does space begin? There's an official line, right? 62 miles up, clean and settled. Not settled at all. That famous boundary, the Kármán line, is usually put at 100 kilometers, about 62 miles, and that's what one international body uses for records. But the United States uses a different number, 50 miles. So whether you count as having reached space can depend on which agency you ask, and the tidy 100-kilometer figure was rounded off for convenience. The man it's named, after never even published the calculation, everyone credits to him. There's no wall up there. No line painted across the sky. The air just thins and thins until there's almost nothing left, and somewhere in that fade we drew a line and called it the edge because we needed one. Which leaves the sun itself. We said it's white like white-hot metal, so it's burning, right? A giant ball of fire in the sky. It isn't on fire at all. Fire is combustion, and combustion needs oxygen, and there's no oxygen out there for it to burn. The sun isn't burning anything. Deep in its core, under crushing pressure and around 15 million degrees, hydrogen is being squeezed so hard that its nuclei fuse into helium. And every time they do, a tiny sliver of mass turns into a staggering amount of energy. That's fusion, not flame. The sun doesn't burn. It converts itself, atom by atom, into light. And that glow, that clean white light, is just the surface heated to thousands of degrees, shining the way white-hot metal shines. No fire. No fuel in the way you picture it. A star quietly turning matter into brightness. And maybe that's the real lesson hiding in all of this. Space keeps refusing our clean stories. The gravity that never lets go, the cold that won't take your heat, the edge that was never really there, the fire that was never fire. We keep drawing simple lines across it, and the universe just keeps quietly stepping over them.